welcome to this problem walkthrough. Today, we'll explore an exciting graph-related problem titled Largest Color Value in a Directed Graph. We'll take a deep dive into the approaches, challenges, and solutions for this problem. Let's get started. In this problem, we are working with a directed graph that contains n nodes labeled from 0 to n1. Each node is assigned a color, represented by a lowercase English letter. These colors are provided in a string called colors, where the character at position I corresponds to the color of node I. The graph itself is defined by a set of directed edges, given as a 2D list called edges. Each edge is represented as a pair, A, B, indicating there is a directed edge from node A to node B. The task is to analyze valid paths within this graph, where a valid path is a sequence of nodes connected by directed edges. For any valid path, the color value is the maximum frequency of any single color along that path. Our goal is to determine the largest color value among all valid paths in the graph. However, if the graph contains a cycle, no valid path can exist, and we return -1. The output of this problem is an integer. If the graph contains at least one valid path, the output is the largest color value for any of those paths. If the graph contains a cycle, the output is -1. Let's consider an example. Suppose the input string colors is abaca, and the edges are defined as 0, 1, 0, 2, 2, 3, 3, 4. In this scenario, the path 0, 2, 3, 4 contains nodes with colors aka. The color appears 3 times in this path, which is the highest frequency of any color within any valid path. Thus, the output for this example is 3. Now, let's look at another example to understand cases where the graph contains a cycle. If the input string colors is A and the edges are 0, 0, we observe a self-loop at node 0. Since cycles invalidate all paths, there are no valid paths in this graph. Therefore, the output is -1. Similarly, consider an example where colors is BBBBB, and the edges are 0, 1, 1, 2, 2, 3, 3, 4, 4, 1. Here, we can detect a cycle within the sequence of nodes 1-2-3-4-1. Due to the presence of this cycle, no valid paths exist, so the output is again -1. Let's now review the constraints and some edge cases to solidify our understanding of the problem. The number of nodes, n, equals the length of the colors string, and n can be as large as 100,000. The number of edges is also bounded at 100,000. Each edge is a pair, A, B, where both A and B are valid node indices between 0 and n1. The colors string only consists of lowercase English letters. Considering edge cases, if the graph has no edges, such as colors equals ABC and edges equals, then each node is isolated, and the largest color value is simply 1, as each node is its own path. For a graph with a single node, like colors equals X and edges equals, the result is also 1 because there are no edges, and the node itself forms the path. We also need to handle graphs with multiple components. For instance, if colors is XYZ and the edges are 0, 1, 2, 2, we analyze each component of the graph separately. For the first component, nodes 0 and 1 form a valid path, while node 2 has a self-loop, making it invalid. Additionally, consider graphs with repeated colors. If colors is ABAB and the edges are 0, 1, 1, 2, 3, 4, 4, 5, the algorithm should correctly track color frequencies across paths in separate components. Finally, cycles, such as in colors equals ABCD with edges 0, 1, 1, 2, 2, 3, 3, 4, 4, 0, invalidate all paths, so the output must be -1. With these constraints and edge cases in mind, we can now design an efficient solution to solve the problem. To tackle this problem, we first considered 2 main approaches. The brute force method uses a straightforward intuition, traverse all possible paths in the graph, count the frequency of each color along these paths, and identify the maximum color count. However, this approach has significant issues. Graphs can contain cycles, which could lead to infinite loops if not handled properly. Even if cycles are managed, the sheer number of paths in a graph leads to exponential time complexity, making this method impractical for large inputs where the number of nodes can reach up to 100,000. Instead, we focus on a more efficient method, using topological sorting combined with dynamic programming. This approach leverages the fact that the graph is directed, allowing nodes to be processed in a dependency order. By maintaining a dynamic programming table, we can track the maximum frequency of each color for every node as we traverse the graph. However, there are important observations to consider. If the graph contains cycles, topological sorting becomes impossible, making the problem unsolvable. But for directed acyclic graphs, or DAGs, we can propagate color frequencies from parent nodes to child nodes, ultimately computing the maximum color value efficiently. The steps involve detecting cycles using methods like Kahn's algorithm or depth-first search, performing a topological sort, initializing a dynamic programming table to store color frequencies, and traversing nodes in the topological order to update the table and track the global maximum frequency. This approach achieves a linear time complexity of O, n plus m, where n is the number of nodes and m is the number of edges, making it robust and scalable. This approach offers several advantages. It is highly efficient for large graphs and addresses the problem constraints effectively. However, it does have some disadvantages. Implementing cycle detection and topological sorting requires careful attention to detail, which adds complexity to the solution. Despite this, the chosen strategy is the topological sort combined with dynamic programming. This method is optimal because its linear time complexity handles the problem's constraints while ensuring correctness. It is well suited for this problem for several reasons. First, cycle detection is a core requirement of the problem, as we need to return -1 if a cycle exists. Topological sorting naturally incorporates cycle detection, making it an ideal choice. Second, brute force methods are computationally infeasible for large inputs, so we need an approach that scales efficiently. Finally, the dynamic programming component allows us to compute the maximum frequency of any color along a directed path without explicitly enumerating all possible paths. Altogether, this strategy balances efficiency and correctness, making it the right choice for solving the problem within the given constraints. When implementing this solution, there are some trade-offs to consider. Simplicity versus efficiency is one such trade-off. While the brute force approach is conceptually simpler, it fails for large graphs due to its exponential time complexity. On the other hand, the chosen approach is more complex but scales efficiently for large inputs. Additionally, detecting cycles and ensuring that the graph is a DAG are prerequisites, which add to the implementation complexity. However, these steps are essential for solving the problem accurately. A key realization in this approach is that the problem can be reduced to operations on a directed acyclic graph, enabling the use of topological sorting to process nodes in a dependency order. Another important insight is that dynamic programming, when implemented with a table indexed by nodes and colors, allows efficient propagation of color frequencies across the graph. Cycle detection also plays a crucial role in ensuring correctness, as it helps identify invalid graphs early on. Ultimately, this strategy strikes a balance between correctness, efficiency, and scalability, making it the most effective solution for handling the problem's requirements. In this problem, we are working with a directed graph where each node has a specific color. The goal is to determine the maximum frequency of any single color that appears along a valid path in the graph. A valid path is defined as a sequence of nodes where we follow the directed edges without revisiting any node. To solve this, the algorithm begins by parsing the input. We represent the graph as an adjacency list, which makes it easy to traverse. For example, if there's an edge from node U to node V, we store V in the list for you. Additionally, we store the color of each node in an array, where the color of node U is stored at colors, U. The next crucial step is cycle detection. Since valid paths cannot revisit nodes, we must ensure the graph is a directed acyclic graph, or DAG. Using depth-first search, we maintain two sets, one for nodes currently in the recursion stack, called visited, and another for nodes that have already been fully explored, called processed. If we encounter a node that is still in the recursion stack, it means there's a cycle in the graph, making it invalid for this problem. Only if the graph is acyclic can we proceed to the next steps. Now, assuming the graph is acyclic, we perform a topological sort to order the nodes in a linear sequence. This ordering ensures that when processing any node, all its dependencies have already been processed. The topological sort can be achieved using depth-first search, storing nodes in reverse postorder. Once we have this order, we use dynamic programming to calculate the maximum frequency of each color along valid paths. To do this, we initialize a two-dimensional array, dp, where dp, u, c, represents the maximum frequency of color C for paths starting from node u. As we process each node in the topological order, we first increment the frequency of its own color in dp. For each of its neighbors, we propagate these frequencies, ensuring that for any color C, the value in dp for the neighbor is updated to the maximum of its current value and the propagated value from the current node. This propagation ensures that color frequencies are properly accumulated along all valid paths in the graph. The final step is to iterate through the dp table to find the global maximum frequency of any color. Several key insights make this approach both effective and efficient. First, detecting cycles early ensures that we respect the problem constraints by guaranteeing no revisiting of nodes. The topological sort provides a clear order to process the nodes, resolving dependencies before moving forward. Dynamic programming allows us to propagate color frequencies efficiently while avoiding redundant calculations. For optimization, we track only the colors that are present in the graph, which helps reduce memory usage. In terms of data structures, the adjacency list is used for efficient graph traversal and storage, while the 2D dp table tracks color frequencies for each node. Sets are utilized for cycle detection, and the topological order is stored in a list. Analyzing the complexity, cycle detection, and topological sorting both run in O, V plus E, where V is the number of nodes and E is the number of edges. The dynamic programming step has a complexity of O, V asterisk C, where C is the number of unique colors. Combining these, the overall complexity of the algorithm is O, V plus E plus V asterisk C, which is highly efficient for this problem. Let's consider some edge cases that the algorithm must handle. First, a graph with no edges is straightforward since each node stands alone, and the result is simply the frequency of its own color. For a graph with a single node, the answer is again the frequency of that node's color. Another scenario involves multiple nodes sharing the same color, which is common and requires the algorithm to correctly propagate and track these frequencies. Finally, in highly connected graphs with large numbers of nodes and edges, the algorithm's efficiency becomes critical to handle the scale. To illustrate the algorithm, let's walk through an example. Imagine we have a graph with 5 nodes and directed edges forming a linear sequence, 0, 1, 2, 3, 4. Each node is assigned a color. Node 0 has color 1, node 1 has color 2, node 2 has color 1, node 3 has color 3, and node 4 has color 1. The task is to determine the maximum frequency of any color along valid paths. We begin by constructing the adjacency list for the graph as follows: node 0 points to node 1 points to node 2, and so on, until node 4, which has no outgoing edges. Next, we verify that the graph contains no cycles, which is true in this case. Performing a topological sort results in the order 0, 1, 2, 3, 4. Now we initialize the dp table with zeros, where each row corresponds to a node, and columns represent color frequencies. Processing nodes in the topological order, we start with node 0. Its color is 1, so we increment dp 0, 1 to 1. For node 1, its color is 2, so we increment dp 1, 2 to 1 and propagate the frequencies from node 0. Repeating this process for all nodes, we eventually update the dp table to reflect the maximum frequencies for each color along all valid paths. Finally, the result is the maximum value in the dp table, which in this example is 3, corresponding to color 1. This demonstrates how the algorithm efficiently solves the problem while respecting all constraints. To solve the problem, we start by importing the necessary modules and defining the largest path value function. We use a defaultic to construct the graph's adjacency list and another defaultic to keep track of the integrity for each node. The adjacency list helps us represent the directed edges between nodes, while the integrity count allows us to determine which nodes have no incoming edges. Next, we iterate through the given edges to populate the adjacency list and update the integrity of each node. Moving on, we initialize a color_count table, which is a 2D list where each row represents a node and each column represents a color from A to Z. This table will be used to track the frequency of each color along the paths leading to a node. We also set up a deque for topological sorting using Kahn's algorithm. Nodes with an in-degree of 0 are added to this queue, as they are the starting points in the graph. Finally, we initialize two variables, visited_nodes to count the number of nodes processed and max_color_value to store the maximum color frequency found so far. The while loop is then set up to process nodes in topological order. Inside the loop, we increment the visited_nodes counter as we process each node. For the current node, we determine its corresponding color in the color_count table by calculating the index of the color using ASCII values. We then update the frequency of this color for the current node and check if this value is greater than the current max_color_value, updating it if necessary. Next, we iterate over the neighbors of the current node. For each neighbor, we update its color_count table by ensuring that each color frequency is the maximum of its current value and the value carried over from the current node. After updating the color frequencies for the neighbor, we decrement its in-degree. If the in-degree of the neighbor becomes 0, it means all its prerequisites have been processed, so we add it to the queue for further processing. After processing all nodes, we check if the visited_nodes count matches the total number of nodes, n. If not, the graph contains a cycle, and we return -1. Otherwise, we return the max_color_value, which represents the largest frequency of any color in any valid path. Here, we start by defining the basic structure of our solution. First, we import the required Java utilities and declare our solution class along with the method largestPathValue. The method takes two inputs, a string colors representing the color of each node and a 2D array edges representing the directed edges in the graph. Inside the method, we determine the number of nodes, n, based on the length of the colors string. We then initialize an adjacency list graph as an array of lists to represent the directed graph and an in-degree array to keep track of the in-degree of each node. Next, we build the graph by iterating over the edges. For each edge, we add the destination node to the adjacency list of the source node and increment the in-degree of the destination node. Additionally, we initialize a 2D array color count to track the frequency of colors along paths for each node, and we create a queue to help with the topological sort. Finally, we add all nodes with 0 in-degree to this queue, as these nodes will act as the starting points for our graph traversal. Once the queue is populated, we proceed with the topological sort using Kahn's algorithm. We initialize two variables, visited nodes, to count the number of nodes processed, and max color value, to keep track of the maximum frequency of any color along any path. As we process each node from the queue, we increment the visited nodes counter and update the color frequency for the current node by incrementing the count corresponding to its color. This is determined using the ASCII value of the character minus the ASCII value of a. We then update max color value to ensure it reflects the highest frequency observed so far. For each neighbor of the current node, we iterate over all possible colors and update the neighbor's color count array by taking the maximum value between the current and propagated frequencies. After processing a neighbor, we decrement its in-degree. If the in-degree of a neighbor becomes 0, we add it to the queue to process it in subsequent steps. This ensures that nodes are processed in the correct topological order. Finally, we check if all the nodes in the graph have been visited during the topological sort. If the number of visited nodes is not equal to n, it means there is a cycle in the graph, and we return -1 as the result. Otherwise, we return max color value, which represents the largest frequency of any color observed along any valid path in the graph. This concludes the implementation of the solution, which efficiently combines graph traversal with frequency tracking to solve the problem. In this example, we are given a directed acyclic graph with nodes representing colors and edges representing directed relationships between these nodes. The input specifies the colors as abacate and the edges as pairs of nodes, such as 0, 1 and 0, 2. First, we construct the graph representation using the edges. This gives us a mapping where each node points to its neighbors. For instance, node 0 points to nodes 1 and 2, while node 2 points to node 3, and so on. We also calculate the in-degrees, which indicate how many edges are pointing into each node. For example, nodes 1, 2, 3, and 4 all have an in-degree of 1. Next, we initialize our state, a color frequency table to keep track of how many times each color appears in paths leading to a node, a queue to process nodes with an in-degree of 0, and variables to count visited nodes and track the maximum frequency of any single color encountered so far. Now, we begin processing the graph in topological order, updating color frequencies as we go. Starting with node 0, which is color A, we increment the frequency for A at node 0, setting it to 1, and update the maximum color value to 1. Then, we decrement the indegrees of its neighbors, nodes 1 and 2, and add them to the queue as their indegrees become 0. Next, we process node 1, which has color B. Here, we increment the frequency for B at node 1, setting it to 1, while the maximum color value remains unchanged. Moving to node 2, which also has color A, we propagate the color frequencies from node 0 to node 2. This means the frequency of A at node 2 becomes 2. The maximum color value is updated to 2. We then decrement the indegree of node 3 and add it to the queue. For node 3, which has color C, we propagate the frequencies from node 2, increment the frequency for C at node 3 to 1, and add node 4 to the queue after updating its indegree. Finally, we process node 4, which has color A, and propagate the frequencies from node 3. At node 4, we update the frequency of A, resulting in a value of 2, which matches the current maximum color value. After processing all nodes, we perform a final check to ensure every node in the graph has been visited. Since the count of visited nodes equals the total number of nodes in the graph, we confirm there is no cycle. The output for this example is 2, as the maximum frequency of any single color, specifically A, is 2. In the next example, we examine a graph with a cycle to understand how the algorithm handles such cases. Here, the input specifies a single node with a self-loop. In this cyclic graph example, the input indicates that the graph consists of a single node, 0, with a self-loop. We construct the graph, which results in node 0 pointing to itself. The indegree calculation shows that node 0 has an indegree of 1. Since there are no nodes with an indegree of 0, the queue remains empty. This means no nodes can be processed, and the count of visited nodes remains 0. At this stage, we detect a cycle in the graph because the number of visited nodes does not match the total number of nodes. The algorithm concludes that the graph contains a cycle, and the output is -1, indicating the result is invalid due to the presence of a cycle. For the final example, we analyze a disconnected graph where not all nodes are connected to each other. The input specifies the colors as ABC and the edges as a single pair, 0, 1. First, we construct the graph, which shows that node 0 points to node 1, while node 2 remains isolated. The indegree calculation indicates that node 1 has an indegree of 1, while nodes 0 and 2 both have an indegree of 0. This means both nodes 0 and 2 can be added directly to the processing queue, as they have no incoming edges. With this initial setup, we are ready to process the graph. We start the topological sort by processing node 0, which is color A. We increment the frequency for A at node 0, setting it to 1, and update the maximum color value to 1. Next, we process node 2, which has color C. Since node 2 is isolated, we simply update the frequency for C at node 2 to 1. Finally, we process node 1, which has color B, and update the frequency for B at node 1 to 1. After processing all nodes, we perform a final check to ensure every node in the graph has been visited. The count of visited nodes matches the total number of nodes, confirming there is no cycle. The output for this example is 1, as each color appears with a maximum frequency of 1 in their respective components of the graph. To analyze the time complexity of this solution, we start by considering the main steps involved. First, constructing the graph requires iterating through all the edges to build the adjacency list and indegree dictionary. If there are m edges, this step takes m time. Next, we initialize the color frequency table, which has n rows, 1 for each node, and 26 columns to represent the letters of the alphabet. Setting up this table takes 26n, which simplifies to O(n) in big O notation. Then, we perform a topological sort using Kahn's algorithm. Each node is processed once, which costs O(n), and we iterate through all edges to update indegrees and propagate color counts, adding another O(m). Now, focusing on the color count propagation step, for each node, we update the color frequency table for its neighbors. Since there are 26 colors, each update involves iterating through these 26 entries. As each edge is processed exactly once, the total cost for this step is 26m. When we combine all these steps, we have O(m) for graph construction, O(26n) for initializing the color frequency table, O(n plus m) for the topological sort, and O(26m) for the color propagation. Adding these together, we get O(26n plus 27m), which simplifies to O(n plus m), because constants like 26 and 27 are ignored in big O notation. This gives us a final time complexity of O(n plus m) for the entire solution. For space complexity, the first consideration is the graph representation. The adjacency list, which stores all edges, requires O(m) space in the worst case. Additionally, the in-degree dictionary, which holds one integer per node, uses O(n) space. The second major contributor is the color frequency table, which contains 26 integers for each of the n nodes. This results in a space usage of O(26n), which simplifies to O(n). Finally, we account for the queue used in the topological sort. In the worst case, all n nodes could be in the queue simultaneously, requiring O(n) space. These are the main components of space usage in the algorithm. When we combine the space requirements, we get O(m) for the adjacency list, O(n) for the in-degree dictionary, O(n) for the color frequency table, and O(n) for the topological sort queue. This results in a total space complexity of O(m plus n plus n plus n), which simplifies to O(m plus 3n), and further reduces to O(m plus n). Now, analyzing the best, average, and worst cases, the algorithm consistently runs in O(n plus m). In the best case, the graph is a directed acyclic graph, DAG, with minimal edges, and the algorithm completes efficiently. In the worst case, the graph is still a DAG but contains the maximum possible number of edges, a complete DAG. Even in this scenario, the algorithm's complexity remains O(n plus m). If a cycle exists, the algorithm detects it and terminates in O(n plus m), maintaining the same overall complexity. Comparing this optimized solution to a brute force approach highlights its efficiency. A naive method would involve exploring all possible paths in the graph and calculating the maximum color value for each path. This would lead to an exponential time complexity of O(2 to the power of n), which becomes infeasible for large graphs. In contrast, the optimized solution leverages Kahn's algorithm for topological sorting and dynamic programming with the color frequency table. By processing each node and edge only once, it achieves a linear time complexity of O(n plus m). This improvement is essential for handling large inputs, as the problem constraints allow up to 10 to the power of 5 nodes and edges. The optimized approach ensures that the algorithm runs efficiently within these limits, making it practical for real-world applications. When solving graph problems, there are a few common mistakes that can trip you up. First, many people neglect edge cases in graphs. For example, disconnected components, self-loops, or multiple edges between nodes are often overlooked, leading to incorrect calculations or even infinite loops during traversal. Next, overlooking constraints is another pitfall. If you assume the graph is small and write inefficient code, such as O(n cubed) solutions, your approach might fail for larger inputs, especially when constraints go up to 10 to the power of 5 or more. Another frequent issue is not validating input thoroughly. For instance, if your graph assumes only positive weights, but you don't check for invalid inputs like negative weights, it can result in runtime errors or incorrect outputs. Finally, improper DFS or BFS implementations are another stumbling block. Forgetting to mark nodes as visited or using the wrong traversal order can lead to infinite loops or revisiting nodes unnecessarily, which increases runtime complexity. Making sure your traversal logic is solid is key to avoiding these errors. Another mistake to avoid is hard-coding solutions for specific cases. For example, if your code only works with an adjacency matrix and doesn't account for adjacency lists, it becomes inflexible and prone to failure if the input format changes. Now, on the topic of interviews, recognizing patterns in graph problems is crucial. Many of these problems share core techniques, like using DFS or BFS for traversal, or dynamic programming for optimization. Identifying these patterns early can save you valuable time. Additionally, always discuss edge cases with your interviewer. Examples include an empty graph, a single-node graph, or whether the graph is cyclic or acyclic. It's also important to consider trade-offs. For example, think about the space and time implications of using an adjacency list versus an adjacency matrix. If the graph is static, pre-computing results like shortest paths can help optimize runtime during queries. These strategies not only help you write better code but also showcase your thought process during an interview. If you're looking to deepen your understanding of graph problems, tackling related problems can be a great way to practice. For instance, LeetCode 133 focuses on cloning a graph, while LeetCode 207 involves detecting cycles in a directed graph, as seen in the course schedule problem. LeetCode 323 looks at counting connected components in an undirected graph, and LeetCode 785 explores whether a graph is bipartite. Each of these problems builds on core graph concepts. Now, exploring alternative approaches can also be helpful. For example, use BFS instead of DFS for shortest paths in unweighted graphs. BFS avoids stack overflow since it's iterative, though it may use more memory than DFS. For path-related problems, dynamic programming with memoization can store intermediate results, reducing redundant calculations at the expense of higher space complexity. Union find is another powerful technique, particularly for determining connected components or detecting cycles in undirected graphs. Though it's less intuitive for path enumeration, it's highly efficient for connectivity problems. A critical tip for working with graphs is to always verify the graph's representation, whether it's an adjacency list, adjacency matrix, or another format. The choice of representation can significantly impact your algorithm. For example, certain algorithms are more efficient with adjacency lists, while others might be better suited for matrices. If there's a mismatch between the algorithm and the representation, it can lead to incorrect or inefficient solutions. Taking the time to adapt your approach based on the graph structure ensures both accuracy and optimal performance in your solution. Thank you for joining me on this walkthrough. We explored the problem largest color value in a directed graph, discussed the brute force approach, and highlighted key takeaways. Don't forget to practice more graph problems to strengthen your skills. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!